Good afternoon, everybody. I'm Michael Hayden from the University of Sydney, and I'm going to talk to you about chemical clocks and chemical tagging with GALAH. So why do we want to do this? Well, ages are kind of the holy grail for galactic archaeology, but it's really, really hard to measure ages for most stars. And so I'm kind of highlighting that fact here with this plot on the right, showing an HR diagram with isochrones overlaid on top. And the isochrones range from 13 gigayears in the bottom right, going all the way up to 1 gigayear in the top left corner, and they're spaced by 1 gigayear increments. And so what you notice is on the main sequence here, all the isochrones are laid on top of each other. So it doesn't matter how old the star is. When you're on the main sequence, you really can't tell how old the star is based on its stellar parameters. Same thing on the giant branch. You see all the isochrones are still pretty closely packed together. So it's really, really hard to measure an age for a star that's a giant. And it's only in this special region here that I've highlighted with this orange box on the turnoff where you can get accurate ages. And so this is why GALAH is really good, because we've been focusing specifically on these stars. But generally, when you do a survey, you're not going to be able to get ages for a lot of the stars you observe. And so maybe chemical tagging can come to our rescue and allow us to solve this problem. So what is chemical tagging? So this is the idea that stars contain the chemical imprints of the gas from which they formed, and also that stars that are born together share the same abundance patterns. And so the idea is if you can measure enough different chemical abundances, you actually can tag stars back to where they were born just on these abundances alone. So we're basically using galactic chemical evolution to act as our age tracers. So if we measure a bunch of different abundances, they act as these age tracers or chemical clocks, so we can get the age for the star. And so we just saw a version of this plot from Chin, but this is kind of the thing that underpins all of what we do. And so this is our astronomer's periodic table. And the key take home here is that all the elements on the periodic table all come from different metal production sites, and those production sites happen on different timescales. So if we take a look at something like iron, we have a lot of contribution from type 1a supernova. And these are stars that are like low and intermediate mass. And so they don't start to explode as supernova until maybe 500 million years, a gigayear, after you have a star formation episode. Whereas you look at something like magnesium, the primary contribution for magnesium is core collapse supernova. So these are supernova for massive stars. They basically explode instantly after you have star formation. And so if you can measure enough of these different elements, they all come from different production sites, it can actually tell you the specific star formation history that went into making the abundance pattern you observe from the star. So this is what that looks like in practice. Again, we saw this briefly from Chen. So this is the age abundance trend for magnesium to iron. And so you can see that magnesium is a really useful age indicator for these older stars. So old stars are on the left here and young stars are on the old stars are on the right, young stars are on the left, one of those directions. And so you can see you can almost just directly read off the age of the star based on its magnesium abundance if you're old. Unfortunately, magnesium isn't perfect. So you look at the young stars here, the slope of magnesium with age is very shallow. So for stars younger than about 8 gigayears or so, magnesium isn't really going to work as your age indicator. But that's okay. We measure more than just magnesium. There are other elements. And so this now is showing yttrium. So yttrium is an element that comes from AGB stars. It's a neutron capture element, and it takes a long time to ramp up. But the key point is that young stars are very yttrium enhanced. Old stars are yttrium poor. And this is a very sensitive age indicator in this young regime where the magnesium wasn't so good, right? So it looks like yttrium kind of solves the issue we had. And you look at this plot and you say, all right, we're done, right? Yttrium tells us everything we need to know about the age. But this plot has a problem, and that's that it's only got 20 data points on it. And worse, the stars are all solar twins, so they have very similar stellar parameters to the sun and also similar metallicity. So there's no guarantee that this plot actually applies to the whole Milky Way. And so when you try a bigger data set to see if this actually works, not so good anymore. So if you look at very metal-rich stars, so that's stars following the red trend line, you can see that the slope is shallow, right? So the yttrium to magnesium trend with age is not very steep for these metal-rich stars. Now, if you look at very metal-poor stars, so stars less than minus 0.3, and they follow the blue line here. And that's, again, very steep curve. So there's a large change in yttrium with age for these metal-poor stars. So what's happening here? Well, what we think is going on is that the metallicity is reflecting the birth radius of the star. So if you don't know, the Milky Way has a very strong metallicity gradient. So stars born in the inner galaxy are a lot more metal rich than stars born in the outer galaxy. And so what we think we're seeing here is a reflection of different star formation histories in different areas of the disk, which lead to a different trend in our chemical abundance clock. So unfortunately, you can't just fit a simple straight line to it, but maybe there's still enough information in the chemistry to actually keep doing this. You just have to do something a little bit more sophisticated than fitting a single line. So this is something that Sanjeev and I worked on. And so we just went one step further instead of saying, okay, what if we have an additional thing besides just age? What if we have age and the metallicity of the star? Can we learn anything more? And so the idea here is that the age and metallicity together give you the birth radius. So if you think about that, we know that metallicity gradient has been in place in the Milky Way, and we know that it's been changing with time. So if you know a specific point in time and you know the metallicity, that corresponds directly to a specific radius in the disk at that time. And again, I told you before that if we know where the star was born, it should have some specific abundance pattern that's unique to that position. So we're like, all right, if that's true, we should actually be able to predict the abundances based on knowing this birth radius. And so Sanjeev and I made a simple polynomial model to predict abundances just based on this fact. Right? So we say, okay, we know the age, we know the metallicity, the birth radius. Can we predict the measured abundances? And so we did that, and then we compared to GALAH, because GALAH tells you the age and the abundances for all these elements. And so that's what's shown in this slightly terrifying figure. But it's only scary because there's so many panels, right? So this highlights the strength of GALAH, that we measure a bunch of different elements, right? And the key take home here is that what GALAH measures are in different colors for different metallicities. And then what we predicted from our simple model was in black. And for, I would say, about 85% of the elements on this plot, the colors in the black line match up perfectly, okay? And there's only a few little strange ones like lithium that we already heard a lot about that don't work, right? And so we know that there's special things with lithium regarding stellar evolution, which is why it doesn't quite match our galactic chemical evolution plot. But this is very encouraging, right? So actually all you do need is that birth radius, that age and the metallicity, to estimate the abundances to really high precision. All right, I'll skip this in the interest of time, but it's really cool font. Yeah. So GALAH is really offering us a way forward. And so what we can actually do is turn this idea around, right? So we just said if the age and metallicity define the abundance plane, the abundance and metallicity should define the age plane. And so GALAH offers us a way to test this because we measure all these different abundances and we have a huge sample of stars with ages. So you can take these turn-off stars and throw them into your favorite machine learning algorithm and feed it all of these age abundance trends that I have here and say, can we learn the age based on these chemical abundances? And so you can use a neural network. I use XGBoost, which is kind of like a decision tree algorithm. And I fed it 13 abundances that GALAH measured. So metallicity, yttrium, barium, so on. And what you see is from this test set that wasn't involved in generating the model, how well we do. So the predicted age based on its chemistry is on the y-axis, and the isochrone age from the turn-off matching is on the bottom x-axis. And you can see we actually did a really good job. So for the bulk of the GALAH survey, the uncertainties in the ages might be the age of the universe. But in this plot, we actually get the age to about 1 gigayear accuracy, 1.5 gigayears, which is actually the uncertainty in our isochrone ages to begin with. So we essentially recover our isochrone age trends. So this is really, really encouraging because now we're saying for every star we observe with GALAH, we measure all of those elements so we can get the age for everything we observe. And so the last thing is you might be interested in knowing which elements matter. So for like future surveys, what elements should you focus on measuring? And it turns out there's actually no real surprises here. The top two are magnesium and silicon. So these are alpha elements coming from core collapse supernova. And we already showed that they immediately tell you whether a star is young or old. Next on the list is yttrium. And so this is our S process abundance that comes from these AGB stars. Next on the list is oxygen, which is another alpha. And the next on the list is barium, which is another S process. So basically it says, if you measure a couple alpha elements, if you measure a couple S process elements, you should be able to get a really good handle on what the age of your star is. And I'll leave you there for my summary.